Hello everyone. So today we are going to talk a little bit about the Z-scores and briefly introduce the normal distribution. So let's just imagine I have 10 students in the class. That's the exact total number of students. It's not a sample. I'm not taking a sample of 10 out of 50. I have 10 students. This is it, okay? I gave them a test and these are the scores. They're not in order. I just put them in, okay? I figured out the mean. I'll talk about this a little later in a minute. I found the mean, which is add these numbers and divide by 10. I got 83 points. Don't forget the units. The standard deviation turned out to be 11.45 points. Remember, the standard deviation is how far are these guys away from 83 on average. For example, this is 3 units away below. This is 13 units away below. This is 8 points below. That's 7 points above. That's 17 points above. But on average, all of them, on average, they are about 11.45 points away on average from the mean. Now you can compute these very quickly by going to stat edit, put these under L1. You don't have to put them in order, just put them in this order if you want, and go to one var stats, and you get that for free, and you get that for free. Now, last time when we first met, we talked about the mean, and we gave it a symbol called X bar, and on the TI, it's going to give you 83, and it's going to give you X bar, if you remember. I am calling it this letter mu. Sounds like this, mu, okay? Mu. Mathematicians, sometimes they call the mean X bar, sometimes they call it mu. And the reason they do that is because when I say X bar is 83 points, I mean the mean is 83 if you are working with a sample. If this was a sample, then we call it X bar. However, if you are dealing with the entire population, we call it mu to distinguish. This is a way for me. So when I read this, I say to myself, okay, this is the mean, which means add these numbers, divide by 10, but I also know that this is my entire class. That's the entire population. This is not a sample of a bigger class, okay? So that's how we distinguish between whether you're working with a sample or working with a population. So in our case, we are working with the entire population. Now I want to pause here because there is a misconception out there about how do you know? How do you know whether you're dealing with a sample or the population? And a lot of students think that if the number is small, like in this case it's 10, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. They think I'm working with a sample. And if they see 50,000, they say, oh, that must be the population. Not necessarily true, okay? So don't let the number of observations deceive you. You could go to a little town of 200 people and you ask for their age, all of them. That would be the entire population of 200. And if the mean age is 65, you better call it mu. Why? Because that entire population has 200 people. Conversely, you can go to a soccer stadium where there might be like 100,000 people, and you take a sample of 1,000 people and ask for their age, and you compute the mean. And let's say their age, the average age is 30, so you can call it 30 years old, and in that case, it's X bar. Even though N was 1,000. And this is called the population mean, even though N was only 200. Okay, so even though this number is much smaller than that number, it doesn't mean you were dealing with the sample and in here you were dealing with the population. In fact, it's quite the opposite. I have a village and the entire population of people that live in that village is 200 people. And I asked each one of them, what is your age? What is your age? So I computed the mean. I better call it mu. I cannot call it X bar. Conversely, at this stadium of 100,000 people, the game just ended, and I took a sample of 1,000 to interview them because I don't want to ask 100,000 people. That is still a sample, even though N, the size, is large compared to that one. Okay, so don't let the number deceive you. All right, so I'm going to move on. And just to reiterate, I said this is my entire class. So don't tell me, well, it's only 10 of them. Why do you call it a population? That's my population. I have 10 students in my class, okay? So let's continue now. How do we find the Z-score? The Z-score, I'll talk about how do we find it, and then I'll show you one example to show why it is important, or two examples. The Z-score is the number of standard deviations from the population mean, is a particular data point. Whatever point you're interested in. Let's say I'm interested in 73. I'm interested in 100. I'm interested in this score of 95. How far, not only how far is this from 83, how many of the 11.45 is 83 away from 95? How many standard deviations from the population mean is a particular data point? So, for example, let's say I'm interested in this score called 84.45. What is the Z-score that represents this number, this data points, called 84.45? Well, let's see. We know the mean is 83. Well, let's keep adding a bunch of 11.45 until I hit this number. So if I add the first 11.45, I hit it on the spot. So the Z-score that represents 84.45 must be 1. I know this must be confusing, and I'm going to show you how to calculate it. It's very simple, actually. I said, how far, any points, let's say 100. How far is 100 away from 83 if you count by these many steps? So for example, 100 is 17 points away from 83, 17. How many of 11.45 is 17? Well, there's definitely more than 1, but less than 2. So if you have 17, so here is 100, and here is 83. So this is 17. How many of 11.45 are in 17? Well, there is 1 here, that's 11.45, that lands me at 94.45, and then I have a little bit of leftover. So I know my Z-score is going to be about more than 1 and less than 2, because 2 will take me outside of 100. Okay, let's figure that out. It's very simple math, actually. You look at the difference as suspected, 100 minus 83, that gives me the 17, and you divide it by 11.45 to see how many of those 11.45 is 100 away from 83. And I found 1.4847. Does that make sense? Let's do another one. How many of those is 91 away from 83? Well, we do 91 minus 83 just to see the difference. The difference is 8. And if I want to know how many of those are in 8 units, I just divide by 11.45, which is standard deviation. And I got 0.698. Okay? So not quite 1 yet. Now notice that the Z-score for 100 and the Z-score for 91 are both positive. It makes sense because 91 and 100 are above 83 in the first place. So the Z-score that is positive, it means 100 is definitely above 83, right? Conversely, I'm interested in the Z-score that represents 75. We know 75 is less than 83. So we know the Z-score is going to be negative. That's the first comment. Second comment, how many of those is 75 from 83? So we take 75, subtract 83. Notice I get a negative number, and you divide by the number of standard deviations, by the standard deviation. It tells me how many standard deviations is 75 away from 83. It is negative 0.699. Basically, what it says is, here is my 83, here is my mean, and 75 is here. How many of those are in here? Well, if I just subtract one of them, it's going to shoot me out. If I subtract one of them, it takes me all the way to a number below 75. So how many of those are in here? It's this much. It's less than 1. It's just above half of standard deviations. Okay, how many standard deviations? How about 20? 20 is going to have to be a negative number for sure, right? So 0 minus 83 is negative 83, divided by 1145 is negative 7.24. So obviously these are negative, obviously these are positive. Since 20 is so far away from 83 compared to the others, we knew the Z-score is going to be very negative. So it's negative 7 points. There are more than 7 of those to go from 83 to 20. In other words, here is 83. Here is 83. If I subtract one standard deviation, more than 7 times, I'll hit 20. That tells me that 20 is very far away from 83. Now, why do we care? Now we know how to compute the Z-score. And by the way, the formula is simple. The Z-score is just whatever you're interested in, this one, any particular data points, whatever you're interested in, minus the mean of the population divided by the standard deviation of the population. This is the formula. That's all I did to go from 100 to this, to go from 75 to that, to go from 91 to that. This is your x. Okay, so you take your x, subtract your mean, divide by standard deviation. Take your x, subtract the mean, divide by standard deviation. Now, I want to pause here. It's like, okay, you just turned 100 into this stupid number, and you turned 91 into that stupid number, and you turned 75 into another stupid number, and you turned 20 into this number. Why? Why can't I just work with my numbers? Why do I have to go to these silly decimals? There is a reason. If I say to you, is 91 a good score? Well, some of you might say, yeah, for sure, it's better than the average. So, yeah, but how better? So some of you might say, yeah, it's above the average, and it's above by 8 points. That's a lot. Somebody else might say, wait a second, man or lady. What do you mean by a lot? The standard deviation is already 11.45, which is high enough. So 91 is not too far from 83. I bet you, if I ask you in class, is 91 far away from 83? Some of you might say yes. Some of you might say no. How do you decide? It depends on the standard deviation. Imagine my standard deviation is 2, okay? Don't you think that 91 is so far away from 83? Yes, it would be. 91 is a very good score if the standard deviation was 2. Because if the standard deviation of 2, 91 is away from 83 by 8 points, divide that by 2, that is 4 standard deviations. So the z-score will be very high, will be 4. But my standard deviation is very high. So if you ask me if 91 is a good score, I'll say yeah, it's definitely above the average. But how far? Well, not by much, because the z-score is fairly small. The z-score is a better indicator if you want to decide whether 90 is a really good score or not a good score. Now, 20 is really a bad score. Not because 20 is so far away from 83. It is because 20 is so far away from 83, even when you consider a high standard deviation. In fact, the z-score is so low. It's -7, more than 7 standard deviations away from 83. That is definitely a bad score. But 91, it's a fine score, but it's not outstanding because the z-score is not very high. Now, you might argue with me, well, it's like, how do we know that 91 is so far away from 83? We can't just say 8 points is good. Well, you're making the same argument, Mr. Alam, and saying 0.698 is not good. And I'm going to show you why this is not very high. And therefore, 91 is a decent score, I would say, using these two numbers. 100 is a good score. I mean, yeah, it's somewhere between, z-score is between 1 and 2. I would say it's more than decent. This is not a bad score. Even though it's below the mean, it's not bad. You're only slightly more than half the standard deviation below the mean. This is definitely bad, right? Are you with me? So we have to take into account not only the mean, but how many of those is the points away from the mean. How many? There are more than 7 standard deviations below the mean, this number 20 is. Now, I'm going to pinpoint at now these numbers to tell you whether this is not too far, very far, decent, not too far, okay? Now, any natural phenomenon in the world that you can perceive tends to follow a normal distribution. What is a normal distribution? A normal distribution is a continuous distribution, not discrete. It's a continuous distribution that tends to follow this bell-shaped curve. We're going to discuss it in detail next time. But for now, I just bring it up to talk a little bit about these numbers, okay? So let me give you some examples of situations or data that follows a normal distribution. If you take all the people in the world and you look at their heights, I can almost guarantee you they're going to follow this curve, which means the average, let's say for men, the average might be 5'8". Did I say age or heights? It doesn't matter. Both will follow normal distribution. Let's say we're talking about the heights. So it'll be 5'8", and you will have very few extremely tall people, and you'll have very few extremely short people. But the bulk of the population will sit around the mean of, let's say, 5'8", let's say, okay? So people's heights, people's age, SAT scores, ACT scores, number of days of pregnancy, diameter of helmets on people's heads, temperature, you name it, almost anything that is a natural tends to follow a natural phenomenon, follows a normal distribution. And if student scores, let's say, follows a normal distribution, then 83 will be in the dead center, right? The peak, so you have a lot more people right at the average, right? And as you move left and right from 83, the numbers begin to shrink, as you can tell. Now, normal distribution tends to adhere to this rule. Look, imagine you're driving here, okay? It looks like you are steering right. Imagine you're standing right there driving down. You would be steering right. We say that this is concave down. It's facing down. At some point in here, and let's say you're driving and going in this direction, you will be steering left, wouldn't you? So that means at this point, the curve is concave up. It's kind of facing concave up, concave down, concave down, concave up. So somewhere in between here, when you are concave down, steering right, and in here, steering left, somewhere in between, you change the curvature. So in here, for example, I'm steering left, I'm steering right, steering left, steering right. Right there, I change my steering wheel. This is called point of inflection. A point of inflection is a point where you change concavity from concave down to concave up. Right, I would say right here, it looks like I'm changing concavity, because in here I'm still steering right, begin to steer left. Right there is called a point of inflection. And it turns out that the distance between 83, this is 83, and the point of inflection is exactly one standard deviation, one of them, one of the 11.45. In other words, if I go down here, this point has to be 83 plus 11.45, which happens to be 94.45. So now if you can add another standard deviation. You might say, well, I don't have another inflection point. In fact, there is only one. Concave down, concave up. There is no other inflection point, no problem. You just have to find one of them. Because once you find one, you measure this distance and you duplicate it. You just, let's say this is 3 inches, you just keep adding 3 inches. You keep subtracting 3 inches, okay? You just have to find one of them. You could also do it backwards here. Find the inflection points and drop it down and subtract 11.45 from 83 to get 71.55. Or since you already did it here, you measure, you take a ruler, you measure this distance and you just keep duplicating it, right? So that's 1 standard deviation, 2 standard deviations, 3 standard deviations, 4 standard deviations, -1 standard deviation, -2, -3. Guess what? If you were my students and scored 94.45, I bet you are 1 standard deviation away from 83, which means right there, Z would have to be 1. This is X equals 94.45, which means Z equals 1. This reflects Z equals 2. This reflects Z equals 0. Think about it. If my score is 83, and I want to find the Z-score, well, it's going to be 83 minus the mean over the standard deviation. So that means the Z-score is 0. So 83 will give me 0, okay? Let me erase this so you don't get confused. So once I find a point of inflection, that is 1 standard deviation. That's not the standard deviation. That is just 1 unit, 1 standard deviation. You keep adding 1 standard deviation. Z equals 1, Z equals 2, Z equals 3, Z equals -1, Z equals -2. Double check it. Pick this number and do the math here, and you will get, I promise you, you will get -1 for Z, okay? So now I can answer your question here. Is this a high score, 91? Well, 91 is slightly more than half of 1 standard deviation. So if the standard deviation, one standard deviation takes me this far, 91, this is half. So just 91 is just slightly more than half. Maybe here. 91.00. Why? Because the z-score is slightly more than half. So I would say that 91 is not too far away from 83, is it? I know it's a good score. You know, when you hear somebody got 91 out of 100, it's like, yeah, that's great. Yeah, good score. But you have to take into account two things. What was the mean and what was the standard deviation? And if I consider the mean and the standard deviation, 91 is decent. Definitely above the average, the mean, but it's decent. It's not here, right? It's not here. Now 20, by the way, now 20 is not bad because it's so far away from 83. 20 is bad because it's so far away from 83 and it is over 7 standard deviations away. So -1, -2, -3, -4, -5, -6, -7, and some change. -20 turned out to be somewhere in here. Isn't that true? Positive 20. It is so far away from 83. Not because 20 is 63 points below 83. It is because also the standard deviation, it is so many, look, is negative 7.24. I have to go down 7 of those, more than 7 of those to hit 20. So 20 is a bad score, okay? So now I would assume you understand the significance of the z-score. This is small below. This is small above. This is really small. This is decent above. That's what I would say. But just by looking at the numbers, you really couldn't tell. If you say, is 75 is a bad score because it's below 83, it's like, let me find the z-score. Find the z-score, it's not bad. It's somewhere in here, right? It's not even 1 standard deviation away. It's somewhere in here, okay? So that's all I'm going to say about the normal distribution. We're not addressing it yet, but I had to talk a little bit about it to show you how you pass a judgments on scores based on the z-score. Now, I'm going to do an example to show you the significance of the z-score. So consider the SAT math and verbal. Sometimes they call it English or reading, whatever. I call it the non-math. Let's call it verbal. I went on the web and I found the mean score to be, I found the mean score and the standard deviations of both the math and the verbal. So if you take all the students in the US that take the math, the mean is 528. It's not X bar because this is the average for all students who took the SAT in math. And the standard deviation is 117. Seems high, yeah? These are facts. I didn't make these up. I went on the web, and you could go on the web and figure that out. The verbal turned out to be 531, slightly above the math. And the standard deviation is lower. Now, you couldn't say, well, on average, people did better in verbal, right? Just because 531 is more than 528. I can make the arguments, but I can also make the arguments, well, the verbal is better because the standard deviation is also lower. It turned out to be the verbal is better. Why? It has a higher mean and a smaller standard deviation. I could make that argument. I could say, yeah, maybe the verbal, on average, people did better in the verbal because they had a higher average, right? And lower standard deviation. But imagine they had a higher average and a higher standard deviation. You couldn't tell, could you? So imagine this number is 120. One might say, yeah, 531 is better. The other students will say, yeah, but 120 is worse than 117, right? Somebody might make the arguments for math and say, yeah, 117 is much better than 120. And the other students will say, yeah, but their scores is lower, right? If you have one of each, you really don't know. It turned out to be that the verbal is better. Why? Because it checked, it gave a check for the mean, and it gave a check for the standard deviation. That's why, okay? But that's not the point. The point is, imagine you scored 600. You, the students who are listening to me, you scored 600 points, both in math and verbal. Did you do better in math or better in verbal? That's the question, okay? So you cannot tell, especially if this is higher. You couldn't tell if 600 in math is better than 600 in verbal unless you compute the z-scores that reflect this 600 in math and this 600 in verbal to see which is better. So let's see. Let's stick with the math. So I want to know what does 600 mean in terms of z-score in math. So we take 600, subtract the mean in math, divide by the standard deviation of the math. I got 0.615. If I go to the verbal, I take my 600 because you scored 600 in both, okay? So now I'm focused on 600 in verbal, okay? Subtract the mean in verbal, divide by the standard deviation of verbal, I got 0.6634. Now I can compare the z-scores. This is Z for math, and this is the Z for verbal. Would you be looking for a higher z-score or a lower z-score? That's a question for you to ask, to answer. Clearly, you want a higher z-score in our case, right? Because the higher the z-score, the better the grade is, assuming it is positive. If it is negative, you want the z-score to be lower, right? I mean, -2 is better than -3. But 3 is better than 2. Makes sense? So the z-score for verbal is slightly better than the z-score for math. So I would answer and say, you did slightly better in verbal, even though both of your scores are the same. You actually did better in verbal. Couple of questions, and then I'll give you homework. The first one. Is 600 score an excellent score in math and verbal? That's a question for you to answer. Okay? This is not your homework. This is just a question for you to think about. We know you did better in verbal. We know that. But is 600 overall, it doesn't matter if it is math or verbal, is it an excellent score? I would say no. Because the z-score is small. Go back to the normal distribution. If this is let's say we deal with math, 528, 117. 528, 528 and 117. So this is one standard deviation, right? 528 plus 117 is whatever, 546. 645. Okay. In math, the z-score is 0.615. This is one standard deviation. So 600 is actually just slightly better than more than half, so it's here. You couldn't say, well, 600 is so far away from 528 by, 72 points. That's silly because you have to take into account the standard deviation. So I couldn't say that, but the z-score is only 0.615. It's not even one standard deviation. It's 600 is basically sitting not too far away from 528. It's still within the bulk. Make sense? So I wouldn't say 600 is an excellent score in math. And I wouldn't say that's about verbal either because the z-score is fairly small, okay? Definitely better than the mean, than the average, but you're not too far away, okay? It's like you're a little above vanilla. Vanilla means boring, right? You know, ice cream, right? It's just a vanilla, which means boring. It's kind of boring, slightly better than boring. Let's put it that way. Now, Next question, what is the unit for all z-scores? You notice I have been putting points, right? When I went to my tests, I had points here. But notice I just give you the z-score as numbers here, right? What is z-score? Z-score number. So what is the unit for the z-score? Well, the z-score is unitless, it has no units, and here is why. Let the formula do the work for you. So let's say we're dealing with scores here. So this is points. Points minus points is still points, right? Like 5 points minus 2 points is 3 points. And the standard deviation is also in points. So if you divide a point by points, the point disappears. If I divide 5 kilometers by 2 kilometers, I just get a number called 2.5 because the kilometer will cancel. 5 kilometers divided by 2 kilometers, I get a number, a naked number, because the kilometer cancels. But if I have 5 kilometers minus 2 kilometers, it's still 3 kilometers. Don't cancel the kilometer then. So I look at points minus points, it gives me points, and point divided by points disappears. So whenever you compute the z-score, you should never have units. So that's the answer to this question. What is the unit for the z-score? The z-score is unitless. Has no units. Sorry, my handwriting is bad. Okay. This one I'm not going to answer. I just want to ask you to think about it. What percentile are you in math verbal? So you're talking about you who got 600. So we know you are 0.615. Your z-score is 0.615 and 0.66. That's one of the questions we're going to answer later. What percentile? Are you in the top 30th? Are you in the 70th percentile? Are you in the 50th percentile? You can't be in the 50th because you would have to score 6. If you score 600 and the mean is 600, that's fine. But the mean is 528 and you scored 600, so you're definitely above the 50th percentile. But what percentile that is? So that's another question we will be able to answer when we discuss the normal distribution in detail. So I did not answer this question. It's for you to think about, okay? Finally, I want to give you an assignment, and I organized it for you in a table, and here it is. So I went online as well, and I looked at the ACT national exam. This is called ACT. Consider the ACT national exam, everybody, okay, in math, reading, and science. So here is math, reading, and science. The mean, remember it's mu, not x bar, because this is everybody who took the exam. The mean for the ACT is 20.7 for math, 21.3 for reading, and 20.8 for science. Don't say people did better in reading because you have to consider the standard deviation, right? The standard deviations are these three. Notice the math has a lower standard deviation. It doesn't mean people did better in math, because I can make the same arguments and say, well, yeah, but their mean is lower than the reading, right? You got to take both into account, and that's why we look for the z-score, right? What I would like you to do is imagine you, the listener, you got 26 in all subjects. You got 26 in math, 26 in reading, 26 in science. I want you to decide in which exam you did relatively better, just like what we did here, 600. You got 600 in both. In which exam you did relatively better on? So I want you to imagine you got 26 in math, 26 in reading, 26 in science, and you know this is their means, it's given to you, and these are the standard deviations given to you. In which exam you did better or worse? And make sure you explain. And finally, imagine you got a z-score of 2 in science. I'm just focused on science. Your z-score, you don't know your score, okay? You know your z-score is 2. I want you to determine your actual score. In other words, what score will give you z equals 2, okay? So 2 questions, they shouldn't take you long at all. I hope this is helpful, and I'll see you next time.